Okay, so I wanted to address a couple of the questions in the wiki from homework 10.5 to 10.8. And the first question was over question 2, and like I indicated, there were a couple of mistakes, one on my end and one in the solution manual. So I wanted to make sure that those were addressed, right? So the question asks, if a proton were traveling at the same speed as electrons in the previous problem, what would the de Broglie wavelength be? And the mass of the proton is 1.6 times 10 to the negative 27 kilograms. So from the previous problem, the momentum is given in the problem as 1.6 times 10 to the negative 22 kilograms times meters per second. So we can calculate what the speed of the electrons is by rearranging the momentum equation, taking the momentum and dividing it by the mass, and that gives us the speed. So if that is the speed of the electrons, right, if that is the speed of the electrons, and the question is asking, what about protons moving with the same speed? What would their de Broglie wavelength be? What we need to do then is employ the de Broglie wavelength formula, h over p, where p is the momentum. Okay, so the problem is not solved for you, all right, but what you need to do is find the new momentum by taking the speed that the electrons had and multiply it by the mass, right, of the proton, and that will give you the momentum of the proton, and then you can just insert that into the de Broglie wavelength equation, right? And in this case, since this is going to be kilograms, meters, and seconds, you want to use the 6.63 times 10 to the negative 34 joules times seconds value for Planck's constant, as opposed to the 4.14 times 10 to, if I remember correctly, the negative 15 electron volts times seconds. Okay, so you want to use the 6.63 times 10 to the negative 34. All right, so that is problem number 2. Okay, that is problem number 2. Problem number 5 says copper has these two absorption lines, right? One that occurs at 0.154 nanometers and one that occurs at 0.139 nanometers. And from the previous homework, right, we've seen this formula right here. From the previous homework, we saw this formula. Remember that E is equal to H times frequency for electromagnetic radiation, right? E is equal to H frequency, H times frequency. So if I have an energy shift, if I have a change in my energy levels, then that change in my energy levels is also equivalent to the frequency that a photon would either be absorbed with or with which it would be emitted, multiplied by Planck's constant, right? So when electrons in orbitals jump energy levels, those energy levels have an energy difference, and it takes a photon of that exact energy to be absorbed by the atom to kick that electron into a higher energy level. Or if the electron is in the higher energy level and it drops, then a photon will be emitted, and the energy that the electron lost will be equal to the energy that the photon has when it's emitted. But remember that the speed of light, when we're talking about electromagnetic radiation, right, the speed of light is equal to the wavelength of light times the frequency. So that tells us that delta E is equal to, if I solve this for F, then I'm going to get C divided by lambda. So now I just insert C over lambda in for F, and I get HC over lambda. Okay. So that is the generic equation for energy level wavelengths, right? So I can calculate the wavelength of a specific energy gap if I know what the energy gap is. Likewise, I can calculate what the energy gap will be if I know what the wavelength of the absorbed photon or emitted photon is. Okay? So that's where this equation comes from. And so what we can do is apply that to each of these wavelengths. So let's just generically call this 154 nanometer, 0.154 nanometer wavelength, let's call that wavelength A. And let's label this 0.139 nanometer wavelength, wavelength B. So the ratio is the difference between the, or I'm sorry, not the difference, but the quotient between these two energies. Okay? So a ratio is just a division between two numbers. It's one number divided by another number. Okay, that's all a ratio is. And so if I insert this HC over lambda in for each energy level, because I'm talking about energy level A, that means that I'm talking about wavelength A. And if I'm talking about energy level B, I'm talking about wavelength B. But in this expression, H and C are both constants. So in the top energy difference, I have HC divided by lambda A, and that is the same, or I should say that's divided by HC divided by lambda B. So we can write this out perhaps a little bit more succinctly, so it might be a little less confusing, right? So here we have energy gap A, which is going to be HC over lambda A, right? And I'm going to divide that by the energy gap of B. So I'm going to divide that by the energy gap of B. But if you recall, okay, I have a number, right? The energy is just a number divided by another number, but those numbers are wrapped up in fractions, right? So if you recall, if I have something like A over B divided by A over C, okay, that's the form of these fractions. How do I handle that, right? How can I manipulate those? And that's going to be nothing but, if you recall from your basic algebra, if I have a fraction divided by a fraction, an equivalent operation is to take the first fraction and multiply it by the reciprocal of the second fraction. And so that gives me, after canceling the A's, C over B. Okay? So we can use that here. Whoops, I didn't mean to do that. We can use that here, and we can say, okay, this ratio, delta E A over delta EB, is equivalent to HC over lambda A multiplied by lambda B over HC. And those cancel out, and I get lambda B divided by lambda A. Okay? So again, I'm not going to plug in the numbers for you and do the calculation, but that is the result. Okay, I will give you guys that much. So that is how you solve that particular problem. Okay, I hope you found that helpful, and if you have any more questions, please don't hesitate to let me know. All right, we'll see you next time.